detect binary black holes, and then, due to popular demand, discuss how the massive black holes formed in the first place. And this was my schematic diagram, and we were basically just discussing this pre-merger phase yesterday, and the idea that the emission, the two main ideas you should remember from yesterday, is a binary. If you replace a single black hole accreting from a disk by two black holes accreting from a disk, when the two black holes have the same mass as the one black hole previously, then it's equally bright. It's not suppressing its accretion. And moreover, it expected that its luminosity will be periodically variable, either because of hydrodynamics. The binary is like a propeller. It's modulating the accretion itself. Or if the binary is quite compact, and it's moving at mildly relativistic speeds, so let's say 100 Schwarzschild radius or less, which corresponds for massive black holes to periods, orbital periods of a year, then you have Doppler effects, just kinematic effects from relativity, which also imprints periodic modulations. And then we discussed how the simplest way to look for this systematically in large optical surveys, and it's difficult to convince yourself you see periodicity. And then we ended by saying, well, there are two other signatures you expect. One is periodic lensing flares, and also the Doppler effect you could try to verify because it's color dependent. So that's where we were. So let me skip all the slides and just talk a little bit about the future of this. So the I think there will be a major change in this game in the future, because the reason, as you remember, just from a large survey of quasars in the time domain, we couldn't tell for sure that it's periodic, is the noise. It's the stochastic noise, which can mimic something that looks periodic. But that can only be really the case if you don't have enough periods. The current situation is we identified these, let's say, 200-300 periodic quasars with periods of order a year, and where they last maybe 100,000 years. So if you remember the lifetime plot I showed, they're short-lived, and the current surveys allow you to pick these out, but then their orbital periods of order a year, so you can't map many periods. But in the future, there will be large optical surveys which go deeper, have many more quasars. And in fact, the prime example of this I just want to make the point about is the LSST from the Rubin Observatory, which is starting very soon, this year or next year. And it's originally was mostly to find supernovae, but it's very wide, which is very good, because you need very large sample of quasars to find the rare short-lived ones with short periods. Short periods are good because then you have many cycles, and then the noise cannot mimic it. It goes deep. That's also good because it finds lower mass black holes, which we currently don't detect in the large surveys, and those are longer lived. So there should be more of those in the survey that are periodic. Lower mass black holes chirp less rapidly and longer lived. And also the cadence is relatively high. A current plan is something like every few days you get a data point, as opposed to every 2 weeks or so. And so you can look for shorter period, less massive black hole binaries, of which there will be many. And this is a plot to illustrate this. This is if you're explicitly interested in LISA sources, this is the LISA sensitivity curve. I've already showed this plot. These are binaries moving into the LISA band. This is when the orbital period is 1 day, just outside LISA's band. And then this is when the orbital period is 1 year, way to the left. So they're moving slowly here. They spend maybe 100,000 years here, and then they spend much shorter times here, so they'll be rarer. And so one interesting question you should ask, how many periodic sources we should find in LSST, and that's interesting to know. And the very simple way of doing that is to take the luminosity function of quasars. Cheng Chin is a student at Columbia who did this exercise. We have the luminosity of how many quasars we have as a function of their luminosity and a function of redshift. LSST goes deeper, so you have to extrapolate these functions empirically to fainter magnitudes than so far observed. And then there's a very simple argument you can make, which is we think quasars are generally triggered by mergers. So I actually don't think I said this explicitly so far, but I did show you galaxy mergers which drive gas to the nuclei of galaxies. It is commonly believed that quasars are actually activated by merger events, and they're relatively short-lived, of order 10 to the 7 or 10 to the 8 years. Now, if these quasars are produced by mergers, and the same mergers give us the binary black holes, then the number of binaries at a given orbital period is simply given by the number of quasars, the fraction of these quasars which are related to binaries, which is of order unity, hopefully. And then you just take how much time you spend at a given period divided by the total lifetime of quasars. This is an extremely simple way to estimate how many binaries you should see on the sky among the quasars. I mean, there's an alternative way of doing this, of course, which is ab initio modeling. You take your cosmological formation of dark matter halos and galaxies, and you make assumptions how black holes form in them, and then you follow their mergers, and you actually predict in a model the number of mergers. It will roughly have to agree with this if it matches the number of quasars. And this is kind of simple shortcut. And so what you do when you do this estimate, you find that the LSST in total should have between tens of millions up to maybe 150 million AGN. So that's a lot. And one interesting thing about having so many quasars is if this, let's say you have 100 million quasars, and each of which lives for 10 to the 8 years, then if you want to find a quasar that lives only 10 years, that's 1 out of 10 to the 7. So there should be 10 of these 100 million that actually is within 10 years of its merger. Does that make sense? So that means you can even do something really, really cute, which is try to mine this huge LSST database for quasars, which show periodicity, which is of order a day, which are objects that are actually going to merge within the next 10 years and will become LISA sources. And there will be maybe tens of those in the optimistic case. And in any case, there will be many, many sources which will be not merging in human lifetime, but are clearly gravitationally wave-driven, guaranteed precursors of LISA sources. So that's very good. Now, one thing you should worry about, which I think is nice to also discuss, okay, but at these very short separations, do we actually see the same behavior as I discussed so far from the hydro simulations? And that's actually an important question. So let's say there was a cartoon picture 10 years ago or so where it was believed or proposed that you have a circumbinary disk, which we discussed a lot yesterday, and then you have the binary black hole, which when it's at sufficiently short separations, gravitational waves take over, and the in-spiral time due to gravitational waves is much shorter. It becomes shorter than the viscous time of the gas here. And then that would be to zeroth order. You could make a very pessimistic statement, which is this binary runs away. The gas cannot follow if it's coming on the viscous time scale. And then the merger actually takes place in vacuum, so will be zero sources with electromagnetic counterparts. So of course I wouldn't say that if I thought this was the final answer. Let me see. So this, I think I'll just show you a movie. Well, let me show you. So in fact, this turns out a worry that has now gone away, very interestingly. So we repeated this kind of hydro simulations I showed the last 2 days, except that we followed the last month of a merging black hole, where we artificially push together the two black holes as dictated by gravitational wave emission. So this is a movie which shows on the top the surface density distribution and the temperature distribution of the gas. And then this here is the light curve. So this is supposed to be a movie. And you saw that it looks kind of similar to what you saw before, except this binary is shrinking. It's still peeling off these streams, and it's still, the mini disks are still fed by these streams, even though the binary is running away. And in the bottom, you see that there's periodic fluctuations, both on the orbital time scale and on the longer time scale having to do with this gas circulation and the cavity wall. And this actually keeps happening. There's 1 order of magnitude shown here in flux. So there's actually not much of a drop. This is 2 days before merger. This is 1 day before merger. And this is the merger itself. So now you have only one black hole, and you're trying to reform this cavity. So this is actually extremely interesting for 2 reasons. One, even a couple of days or a week before merger, this binary is actually very bright. So you could even have a case where the LISA instrument detected an ongoing merger, and you point your telescope and you know exactly the period that you should be looking for, and it doesn't seem particularly dim. The 4 different lines here are in 4 different, the bolometric, the X-ray, the optical, and the UV. And so, so that's a reassurance that you're not dealing with this runaways picture with no electromagnetic counterpart. And the physical explanation of why the picture was wrong is very simple. The gas actually is not coming on in the viscous time. It's following the black holes on the orbital time, because you're basically like a propeller moving gas around, changing its angular momentum on the orbital time scale of the binary. You're sloshing and throwing gas around. It doesn't have to behave on the viscous time scale. The second exciting thing which looks very promising is that if you look at the green curve here, which is the X-ray emission, it actually is also maintained until the last few hours. But in the last few orbits of the binary, the X-ray luminosity drops here by 4 orders of magnitude, simply because of the fact that if you watch the movie again, eventually it is true that that these disks are the hottest part of this emission, the X-ray, come from the shocked gas that are in these edges of these mini disks, and they do eventually disappear in the last few hours, basically because of the tidal forces from the companion, and because you do eventually run out of these streams that feed them. So if you look carefully, you see that in the last, when the last bit happens, these mini disks disappear and there's no more fueling in the X-rays. In the optical so now it's gone. In the optical and the UV, there's emission still coming from over here, and it still stays there. So this is very interesting. This would be very interesting in the LISA era, where LISA finds an ongoing merger. And if you turn your X-ray telescope, you should see one object in the error box of LISA, which disappears completely in the X-rays from the sky. Yeah, question?
Do you have information if it also vanishes in gamma rays?
So I think actually the answer to that is yes, because the gamma rays would be coming from have to do with the jets, which are powered by the emission, the m dot, and the m dot, the fueling rate also plummets.
Okay, and it happens because it fuses together, so it's just stop in this. Like, could you explain again how exactly why does it vanish?
So we don't have 100% understanding, but basically the tidal, it's almost following simply the tidal. So there's something called the tidal truncation radius, which I actually briefly alluded to in the beginning. Around each black hole, there's a circle, roughly, circular region, outside of which gases or particles are not bound to the black hole. This is just like Roche lobe or Hill radius. And that tidal radius is actually linearly proportional to the separation of the two black holes. And at some point, when the two black holes approach each other, correspondingly these tidal radii are shrinking, and at some point they match the innermost circular stable orbit. So you no longer can have mini disks within this region, so they just vanish. When you look at, I didn't bring these plots, but when you look at the size of this mini disk, it's actually roughly following this tidal truncation, and the shrinkage becomes very rapid at the end.
Thank you.
I mean, there could be some more complications because of how it is true that the cavity wall gets farther and farther from the binary which is running away. The cavity wall itself doesn't really follow. So you're also farther and you're peeling streams less efficiently. So there could be. These things are very hard. There's no real analytic way to analyze. So, but it does look like mostly just simply tidal truncation. Okay, I think I should move on and talk about something else. I think, well, maybe one. I think I won't give you details because I want to get to massive black hole formation. But I did show this plot yesterday, and I also made the point that the gas, when it's dominating the orbital evolution, it drives binaries to an eccentricity of about a half. And so the scenario here is also interesting because this is the eccentricity value where the binaries end up. So hopefully you remember when I discussed this plot. So the idea is that when the gravitational waves take over, which happens around the 100 Schwarzschild radius, becomes stronger than the gas torques, the binary starts circularizing, starting from an eccentricity of 0.5 at 100 Schwarzschild radius. So you can then calculate what should be the eccentricity when you enter the LISA band. And well, these are on the right here. This is the chirp mass. These are binaries, equal mass binaries at different redshifts with this chirp mass. And these are the eccentricities when you enter the LISA band. So low redshift, low mass binary can have, let's say, redshift 1, even a 10 to the 4, 5 solar mass, 6 solar mass binary. We'll have an eccentricity that's not, of course, large, but it's between 0.1 and 1%. So I think that's potentially interesting in the sense that you can discover that these binary inspirals are not circular in LISA. And then that tells you that something made them eccentric earlier on, and you can blame it on the gas disk. Okay. So I should spend at least a little bit of time telling you about other signatures besides this, which I spend almost all my time on, periodicity. There are also possible signatures of binaries which are not in the time domain, but simply based on their spectra. And the idea is to look for how the spectrum of a binary might differ from a spectrum of a single black hole. And well, just to remind you of this picture, I made also the point that this is the template of an average quasar spectrum, which has thermal emission, and then in the radio and then the gamma rays, they have non-thermal emission. And now if you imagine you have a binary stuck into the middle here, you can already start thinking and coming up with ways it will differ from a single black hole, which are well, the most interesting ones for me I listed here. So first of all, in the normal single black hole disk, there's slow viscous inspiral of the accretion disk, and all the emission you see is generated from viscous dissipation. Two annuli of the gas are suffering friction as they shear on one another, which generates heat, which is turned into photons. But here is an other energy source. The binary, as I just described, is throwing gas around and making shocks. These shocks colliding gas streams get very hot. So this is actually hotter in the inner part of these binary disks, near the mini disk edges and the cavity wall and these streams. They tend to be hotter because they're heated by these extra shocks compared to single black hole disk. In fact, here is a composite spectrum just to make this point. This is from an older paper. we decomposed. So you can calculate the spectrum from one of these simulations, and again, few people have done this. There's rough agreement, at least on this effect. So you can simply take your simulation. Each patch is emitting black body radiation at the temperature that you measure in the simulation. And this part, the red, is emission from the outer disk, which is roughly speaking undisturbed, no extra heating from the binary. So this part is similar to a single black hole, except for and then the green part is coming from the gas that's inside this cavity, and then this orange curve is coming from emission from the mini disks. And you can see that, well, if you had just had a single black hole, you would have a spectrum that looks sort of like this. I should have put that on this plot. Here the mini disk and are much hotter, so they extend to much higher energies. So you could actually look for quasars you think are binaries. You can look for their spectrum being much harder. In fact, there have been observational searches, both with Chandra and NuStar, looking at 5 or 6 of these periodically identified sources that are identified as periodic in the optical. Just to tell you that actually it's a null result. Their spectrum doesn't really so far show a clear deviation from a single black hole. So either those are not binaries, or something is wrong with this picture. But I already told you that it's not super surprising. Some or most of the periodic sources that are identified could just be noise. So you have to keep searching. Another idea is broad emission lines. In this picture, as I explained, there's emission coming from recombination of the ionized gas around the black hole. And in the simplest picture, where you have 2 black holes and each one has its own broadline region, so you're replacing this black hole, which is 1 with its broadline region, with another black hole which has its own broadline region bound to it, and it's moving around. Then you should see that the broadline should be offset in velocity if the black holes are moving. And this could be thousands or tens of thousands of kilometers per second in principle. So you can look for AGN with broad lines that are offset compared to the narrow lines. The narrow lines are far away, so they won't care whether there's 2 black holes or 1. So do we a spectral offset. And ideally it should also be moving. These broad lines should be moving with the moving binary components. So you should see broad lines that are shifting in frequency relative to the narrow lines. So there have also been searches for these. There's actually 2 or 3 candidates where people identified shifts which are even changing over time. Again, by itself, those are candidates. By itself, the complications here is that these lines are complicated. We don't fully understand the structure of this broadline region. And so you want to find corroborating evidence. So I think I won't go into details. I just explained that there's another possible signature, which is a particularly useful emission line, the iron K alpha line, which has the property that is already being used to measure spin of the black holes. So I don't know if this was described actually in any of the. So maybe I'll just say something about that, just because this is something already people use to measure black hole spin. So this is from a review by Andy Fabian. This shows that you have an emission. You have just a cartoon picture of this emission line. So this is a gas that's moving around. It's coming towards us on the right, receding on the left. And then these are 2 annuli from which you're calculating emission of this iron K alpha line, which is a line around the 6 point some keV in the X-rays, one of the high lying shells of the iron atom, which is being ionized by the continuum emission and then causing recombination. So if you have a Newtonian disk, you should just have the 2 annuli here give you 2 line shapes which look like this. There are 2 peaks, one on the red side, one on the blue side, if you sum up all the emission along these circles. If you include special relativity, then the blue side will be brighter than the red side because of Doppler beaming and transverse Doppler shifts. So you get asymmetry due to special relativity. You also get then general relativistic effect imprinted on this line because the photons coming further from the black hole are climbing out of a deeper potential well. And and you also shift everything to the red. So you basically reduce the luminosity and move things to the left. And then when you add everything up, you should look like this. So these shapes have been observed. As I said, it's particularly useful because it's probing the spin of black hole. Because if you have a Kerr metric, the gas can extend closer to the black hole, and therefore will have higher velocity motions. So you have broader wings of this line. If you have a Schwarzschild black hole, the gas cannot extend that far in, so you have narrower shoulders, smaller shoulders. And now you can imagine, just for cartoon, that if you have two black holes instead of one, you can modify the shape. So here's an actual prediction in a toy model where we assume that the iron K emission is coming from this circumbinary disk, but now you have two black holes, so you truncate the inner part. And when you truncate that, it's kind of equivalent to, well, it's very similar to what people do with spin measurements already. You're cutting off the highest velocity parts of the shoulders of this line. So you go from something that would look like this, if you had one black hole in the middle with these broad shoulders, and then if you cut it to increasingly large distances, you cut down the shoulders. So you can look for iron K alpha lines which have been cut like that. Now, in the simulations, we also find that this part of the emission is actually, there's more gas there and it's hotter, and perhaps there's more iron K emission from this rim. In that case, you would imprint features that look very telltale. You have these double peaks within the double peaks due to this additional structure with a dense rim. And then I think the most kind of indisputable evidence would be is if the black holes, just like in the broadline case, would have their own iron K alpha lines. This is actually maybe more possible than with the broad lines because the iron K alpha line does come from relatively close to the black holes. So now if you say there's iron K alpha line coming from a moving black hole, then the wings of these lines would be moving from left to right like a seesaw oscillation. Whenever this iron K alpha line is moving away from us, you have an emission on the red part. When it's coming around, coming towards us, then you have an emission on the blue side. So you can look for, these are other signatures of binaries. I think, let's see. So there's two more things I listed here. One is the infrared echo from the fact that if you have a binary over here, and this is the obscuring torus, and in the infrared, you see the emission which is illuminated by the black hole from the optical and UV emission, and is scattered on this obscuring torus and coming in the infrared towards us with a time delay. That has also been measured in quasars, and you can see that that also gets modified in case there's a binary, because the illumination of this torus, it becomes a little complicated. You have a binary which is moving around. So for example, in the example where the binary emission is modulated by relativity because you're 100 Schwarzschild radius, so you're moving at a few percent of speed of light and you have beaming, then it's like you have a lighthouse in the middle. The binary's emission from each component is forward beamed. So inside here, instead of a stationary light bulb, you have a light bulb that's pulsating because the binary's luminosity is periodically fluctuating. And on top of that is like a lighthouse. It's always stronger emission in one direction, forward, ahead of the moving binary. So you're illuminating this, and this lighthouse effect is reverberated and shows up in the infrared echo. So we made toy calculations of this. I think I will maybe not show details, but in principle, that imposes a structure on this echo. The last thing I listed here is polarization, which is also interesting. The light that's scattered from this scattering torus can also become polarized. And then the polarization direction and amplitude will periodically fluctuate following the binary's motion. So that's hard, but again, it's maybe 1% or 10.1% polarization is possible in this kind of models. So I think I want to leave time for one more thing, which is the afterglows, and that will be my last bit about this topic. So if you remember, sorry, if you go back to my overview, I made the point that there's also signatures of binaries which occur after the merger. And these signatures have to do with what I already discussed, the fact that the merging black hole loses mass and recoils, which let me see, where are we? So this just shows the same. I don't know if I have to repeat this, but basically the idea is very simple, at least conceptually. So imagine, for example, over here, that you have a supermassive black hole that's instantly losing few percent of its mass. And by the time of the merger, just before the merger, this was so compact that you can consider, in the simplest case, a test particle that's just going on a circle around the binary. That doesn't really matter that it's a binary. It's so compact that separation is much, much smaller than the distance of this particle from the center of mass. And then when the merger happens, because you reduce effectively the mass of the point source, what would happen? If you think about this, actually I think I could just ask you to tell me what happens. Because suppose you have a Newtonian, this could be homework problem. You have a circular orbit of a massless test particle around the point mass, and then you, not adiabatically, but suddenly reduce the mass by 5%. Then what happens to the orbit? You said... So... Yeah, that's getting warm, but I think there's actually even simpler way of saying this. You have an initial condition where you have a massless test particle going around a mass in a tangential direction. There's no radial component, but it's going too fast, right? Because the mass has been reduced. It's going too fast for a circular orbit by a few percent. That means it must be on an ellipse. In fact, it must be a periapse of an ellipse. So it's going to you're just changing the circular orbit to an elliptical orbit. And on the other side, everywhere the circularly moving particles are now at pericenters of their ellipses. And in fact, these ellipses, you can think of it as epicycles. So if you only look at the radial distance from the black hole, they oscillate. And because we have a full ring of particles, you can basically think I have a ring of particles. After the mass loss, this ring goes like this. The adjacent ring also goes like this, but at a different frequency, right? Because the oscillation frequency is the local Keplerian frequency. So as soon as you have this mass loss, you've imposed a bunch of oscillating rings on the motions, and therefore there will be regions where these rings cross, because the oscillations are out of phase, but there will be particular regions where these oscillations cross. There's a very simple thing about the recoil. The recoil is the same effect. You have a black hole that's kicked, that correspondingly the particle is now kicked in the opposite direction in the frame of the black hole, and so again it's on an ellipse. But now it's a bit different because different directions around the black hole, the particle can be kicked along its motion or opposite its motion, so it could be in different phases of the ellipse. So these oscillations are also has azimuthal structure. So I think I'm going to skip the math. You can actually very quickly estimate where these caustics orbit intersections should happen based on simple arguments, where these oscillations will cause collisions, which I skip. I just show you the more illustrative picture. So this just shows what happens if you put a bunch of test particles initially on circular orbits, and then you this particular plot here is you kick the black hole in the orbital plane. This is you kick the black hole perpendicular to the orbital plane. If you kick it in the perpendicular direction, then now you have elliptical orbits which are tilted because you added a velocity component, a small velocity component to the orbit that's out of the plane. So you're on a new orbit that's tilted. And then those tilted orbits also intersect and cause these caustics. So that's a very interesting signature because, and again, you can analytically predict the locations of these caustics, and you can find that the moves out over time at the kick velocity. You get very simple results that the spiral caustics pattern is moving outward at the velocity of the kick. In fact, this is an old simulation just to show you that, of course, in hydro simulations, this is an example of the gas distribution of a kicked black hole around the black hole kick, and it confirms roughly this pattern. Of course, instead of caustics and orbit crossings, here you get shocks. So you can measure the heating of the gas in these shocks and plot the luminosity as a function of time, and you get that it's actually a very unusual afterglow. These shocks get stronger and stronger, so you get a brightening and also a hardening of the spectrum, which can be quite different from other kinds of afterglows, which tend to fade over time and move to lower and lower frequencies. Here you actually get hotter and hotter shocks because the perturbations from a kick correspond to larger and larger fractions of the orbital velocity for the gas that's further and further away, so you get stronger and stronger perturbations. So these are afterglows. Okay, I should say last topic.
So yeah. Zoltan, how long these afterglows last for?
So actually this, the time scales I listed here. So in the case of the mass loss, you can show that these orbit crossings happen on the local orbital time scale at the gap, times m over delta m. So they start at around a week, and then you can actually last practically as long as you get to the point where gas gets, you reach the edge of the disk, or in the case of the recoil, where the orbital velocity matches the kick velocity and the gas is actually unbound. And so that can start weeks or months for a 10 to the 6 solar mass black hole and last for years.
So if you go back to that plot with the optical UV X-ray and the X-ray becoming silent, that's way far off to the right of that plot?
Yeah, so actually, very good question, because when we did this paper, where is that? Yeah, so we actually wanted to, you're asking a very good question, because when we started doing this paper, we wanted to see if in a real, unlike this toy model that I showed, where you have circular orbits, a nice undisturbed disk and you kick it, do you get the similar signature in a more realistic, already distorted shaped disks? The problem is you're right, we only followed this for a few days and not for weeks or months, just because we didn't have CPU, actually GPU time for this. Exactly. So, so we plug in by hand the kick and the mass loss, and you do actually see in the first few days, you do see small effect with or without the kicks on these recovering light curves, but the effect is so small you can't really try to go for it. If you wait a month, and basically because the gas that's being disturbed very close to the black hole is just doesn't move on coherent circles, so you don't get these nice coherent shocks. I think further out you will. You just at some point you will, but it's just not in this simulation. So I'm eternally late, but I do want to make one last point about binary signatures, because I promised there are 3 things you want to get out of these gas disks. And I talked about the orbital evolution. The gas disk impacts the binary's orbit. The gas disk is nice, it can give you electromagnetic signatures. And then the third topic, which I will very briefly mention here, is that the gas disk, in principle, if it modifies the orbit strongly enough, it could actually affect your gravitation waveform. And should you worry about this, is the question. And again, in the context of LISA, massive black holes, there has been work on this going back, in analytic days. And generally, the answer has been, well, people have considered whether hydrodynamical drag or accretion onto the black holes themselves or this planetary migration would be comparable to gravitational wave in spiral speeds. But I think the general answer is that it's very, very small effects. It's very hard to compete in the LISA band with the very strong gravitational in spiral, because you need to have gas that's comparable to the black hole mass to make order unity changes to the orbit within the orbital timescales. But there's one regime where this seems not negligible. So that's this regime. So let me just show you actually the simulations. So there's one regime where this might be important when one of the black holes is much smaller than the other. So these are the so-called extreme mass ratio in spirals. And this was a thesis of a student at Columbia, Andrea Derzinski. So what she did was again, very similar kind of hydro simulation, but the mass ratio is now changed. So this black hole here was only 10⁻³ of the big black hole here. This simulation is nice because you don't really care to resolve what's going on here. So we can have an inner boundary, and we're just following the gas motion around this secondary. And you see a gap opens. And by the way, so this should be a particular kind of LISA source. I don't know if this came up, extreme mass ratio in spirals. So-called EMRIs is one class of LISA source that's very prominently studied. The specialty of these objects is their chirp mass. If you remember, the chirp mass has to do with the product of M1 and M2. So the chirp mass of such an object is very low, so it's chirping very slowly. So it actually spends a long time in the LISA band. It can be years. And it executes hundreds of thousands or even million cycles in the LISA band. And we just measured the gas distribution and again measured how the orbit is impacted by the fact that there's an asymmetric. If you zoom in over here, this is the gas flow. The gas is actually going around in these horseshoe orbits, and this is in the frame of the small black hole. The gas is passing it in this direction. On the outside, it's passing the other direction. You have a flow pattern, and then you have this bend stuff. And when you add the gravitational forces, there is a torque. And if you convert this to effect on the gravitational wave in spiral, so this here is again the LISA sensitivity curve. These are 3 examples of such EMRIs, which last 5 years. So this object here, and this again, I think is a 10⁶ solar mass black hole and a 10⁵ solar mass black hole. And if in 5 years it would move from here to here, or from here to here, or it would move from here to here, and our simulation that I just showed, it goes from here to here. And here I think there's about 100,000 or a few 100,000 orbits. And this plot here shows as it goes from the left to the right, from 11 to 5 Schwarzschild radii is the separation. This is the gravitational wave torque. And this, everything is scaled with respect to the viscous torque, which doesn't really matter. This is here the torque from the gravity of the gas times 10 to the 4. This is the torque times 10 to the 9 from the accretion on the object. So what this says is the following. You have distortions to this gravitational wave in spiral, which are completely negligible from the accretion. So this is about a factor of 100 times 10 to the 9. This is 10 minus 11 effect. You'll never see that in the LISA band. These gas torques, they're comparable over here to the gravitational wave torques, maybe factor of 2 lower, times 10 to the 4. So this is a 10 minus 4 effect, which means if you have, and here it goes to 10 to the 5 effect. So it's a distortion of the waveforms at the level of 10 minus 4, 10 minus 5. But you have 10 to the several times 10 to the 5 cycles. And that means that you can actually detect this effect. You basically have slightly accelerated in spiral by 0.01%, which means you have few additional cycles in the LISA band. Instead of 300,000, you have 300,006 cycles, and that can actually be detected. And then optimistically, this is very good because, well, you could say that's bad news. LISA might mess up the waveform analysis if you don't take this into account. But optimistically, if you can measure this, then LISA can be turned into an instrument that studies the accretion disks by looking for these subtle distortions. Okay, so that's my last point. So I'm going to stop here before we move. I think my main conclusions are basically takeaway message from this second lecture, protruding in the third lecture, is that binary black holes are very bright and they're strongly periodic if their mass ratio is larger than 1 to 25. And there are some candidates uncovered in quasar surveys, and we still have to prove that they're really binaries. And I think in the future, with large surveys, that will be possible. And we expect these unusual afterglows. So any questions on this part? Yeah.
Thank you. So these time scales correspond to supermassive black holes, or how do they scale with the black hole mass?
So most of what I showed, these simulations, except for the ones where we predict the spectrum, they're scale-free, because you assume the gas has some fixed temperature. So they apply to stellar mass black holes. So if you have a stellar mass black hole with a gas disk around it, binary black hole with a gas disk around it, I think you can basically take the same simulations and apply them. In fact, yeah.
So you're saying that these times you put weeks, hours, are independent on the mass of the coalescing black holes?
Yeah, sorry. So if you this time scale for the afterglows does scale with the mass.
Yes.
It scales.
How is it scaling?
So, for example, the mass loss in these shocks are just happen on the you have to take the orbital time scale of the gas wherever you're trying to look for the shocks.
And this was here correspond to supermassive black holes or to stellar mass?
And this corresponds. Yeah, sorry, I didn't say that. This corresponds to 10 to the 6 solar mass black hole.
10 to 6.
Yeah. Okay. So if you want the stellar mass black hole, you have to reduce this to milliseconds. The orbital time will be, milliseconds times this number, which is 100. So you'll have 100 milliseconds. So maybe up fraction of a second. And yeah.
All right. Thanks.
More questions? Okay.
Okay. So I think I have maybe 40 minutes for my last topic. So we had a vote, and sorry about the stellar mass black holes. Sorry, if I would have discussed in some detail what happens with stellar mass black holes, but they were voted down. So our next question is, where do these massive black holes in galactic nuclei come from anyway? And that's lecture 3. So I wanted, again, I'll have to speed through some of the slides here, but I wanted to just summarize the observational situation a little bit and then discuss ideas where these massive black holes might come from, how they form and become so large in the early universe. And then, because again, spoiler alert is that we don't know. I'm just going to discuss 3 very different ideas, which I think are the leading contenders. So at least a little bit on how in the future we might actually know this. So I'm sure you know the observational situation. We have very different kind of black holes. There's the massive ones I've been discussing, above 10 to the 6 solar mass or so, 10 to the 5 or 6 and higher. There's the stellar mass black holes in between, we don't know. Maybe they are there, maybe they are not. The observations become very difficult because when the black hole is small, the sphere of influence becomes very small and you just can't resolve it usually. We do have a couple of examples of candidate black holes down to almost 10 to the 4 solar masses in some star clusters. The situation is very different in terms of understanding these black holes. Because the stellar mass ones we basically understand, and the massive ones we don't know where they come from. The stellar mass black holes, so just to be on the big picture, to be on the same page, we understand that massive stars, when they die, if they're massive enough, about 25 solar mass or higher, when they die, they leave behind the black hole, and these birth masses are limited to few solar masses, up to about 60 solar masses. So the heaviest stars, when they die, they explode as pair instability supernovae, and they cannot leave black holes more massive than this range of 60 solar masses. There's actually, I will mention later, the supermassive stars which can give you more massive black holes above this, well above this limit. In a typical galaxy like the Milky Way, we expect 100 million stellar mass black holes, because roughly, if you take the IMF of stars, mass distribution of stars, 0.1% of them are above 25 solar masses. So if you have if you have 10 to the 11 stars in the Milky Way, 10 to the 8 of them will leave a black hole. And of these 100 million, we only detected a few dozen. And in fact, it's kind of interesting because we don't detect single stellar mass black holes. We only detect them when they have a companion, either a star, a stellar companion, in which case the black hole is lit up by an accretion disk powered by the pulling mass of the companion star. So then it's called an X-ray binary. And we have a few dozen examples of these. Or if they have another black hole partner, which we discussed a lot, detected in gravitational waves. But it's kind of still interesting. We probe this 100 million through detecting a few dozen when they're in binaries. We don't really have ways to detect single black holes floating around in the Milky Way. And we only see these in the relatively nearby universe, although LIGO keeps extending its horizon to nearby galaxies. Now, the massive black holes situation is very different. Again, instead of 100 million, we just have 1 or maybe 2 or 3 in the nucleus of every galaxy. The mass of these is comparable to the total mass of stellar mass black hole remnants, because it's a few times 10 - 4 of the stars in the galaxy. The masses that have been detected are in this range. And again, it's similar to the stellar situation. We have about 100 black holes which we directly detected. I already discussed this in nearby galaxies, and we have a couple of black holes imaged directly in the radio. 1% of these nuclear black holes in galaxies roughly are active and act like quasars, so we can see those very far away. And then we don't actually understand where they came from, these massive black holes. Now, everybody knows quasars, they're fueled by the accretion disk, but there's a couple of interesting points. in terms of understanding where the black holes come from. The first one is that, as I already showed, there's the evolving luminosity function of quasars. And this goes now out to redshift 7 from the Subaru telescope, which surveyed something like 150 square degrees to quite deep depths. So these black holes, and the faintest ones, have masses of about 10 to the 8 solar masses. And then what you see here is the number of black holes is increasing over redshift. But this evolution is consistent with having in the early universe already placed million solar mass or so black holes in the nuclei of these galaxies. And then those grow by accretion, and perhaps mergers play a role. But we, in fact, this is critical. We know that most of the mass of the black holes residing in the nuclei of galaxies in the local universe has come through accretion into the black holes of these powering these quasars. So the argument here is actually called the Zoltan argument, and some people think that's me, but it's actually not. This person is much older than me, and Zoltan is his last name, not his first name, and he's from Poland. But he wrote this amazing paper in '91, where he did something super simple. He said, all these quasars are here, all the light that's coming out of these quasars is essentially epsilon m dot c squared, where epsilon is some radiative efficiency, and is related to the mass fueling these objects. So if epsilon m dot c squared comes out as light, 1 minus epsilon m dot is growing the black hole, then if you integrate over time the emission from all the quasars, then you find the total mass that was accreted by the population of black holes. So you take this luminosity function at all redshifts, you sum up and integrate over both luminosity on the x-axis, and you integrate over time. You have the total light per unit volume emitted by these objects. And the only thing you need to put in is a radiative efficiency, which is generally actually known to be about 10%. And then you can compare it to the total mass in galactic nuclei in black holes in the nearby universe. Does this argument sound clear? So this argument says that all the black holes that we know now have been accreted in these quasars. So the seeds that were existing before must have been there earlier, and then the rest of the evolution is just growth by accretion. This is the luminosity of a quasar. So there should, sorry, I missed the c squared. This should be dm dt times c squared. Yeah. Okay. Now the second point about quasars is that it allows us to go to high redshift and find these high redshift quasars. So this we've compiled in this annual review article a few years ago. There was at the time about 200 quasars, now there are about 300 around redshift 6 or earlier from these various surveys. This is the masses of these black holes, generally inferred from the width of their broad lines, for the ones for which we have spectra, or else just from assuming some Eddington ratio. So these are actually going down below even 10 to the 8 solar masses, although most of these don't have spectra. And then the redshift winner is here, 7.6. Now, what caused a lot of consternation for the last 20 years, and many papers have been written about the fact that these masses are already very high, and the universe here is very young. This is the age of the universe. Here it's only 700 million years old, and we still have these billion solar mass black holes. And the question is how that is possible. Now, there are two curves here which shows the maximum mass. If you assume, I hope you know what I mean by Eddington limit, but this assumes that I have a redshift 35, a 10 or 100 solar mass stellar black hole remnant that's continuously growing at the Eddington rate. I think Actually, can you raise your hand if I need to explain the Eddington rate? Okay, so I'll explain that in 5 slides. There's a maximum rate, we think, at which black holes might be able to grow. If you grow at that maximum rate, this would be the mass of your black hole, which started its life at redshift 35, which is when we think the very first stars in our Hubble volume might have been appearing. And what you see is, well, these 3 actually you can't even really explain. Even if you start with a 100 solar mass black hole, and even if you uninterruptedly grow at all times. But even these are actually a little hard to conceive, that this continuous growth at all the time from a stellar mass seed. I mean, the stellar mass seed would be the simplest idea, because we know stars leave behind black holes. It's just that you can't just take a star and grow it and produce these quasars. So how do you solve this problem? Well, again, I could ask you, what are the solutions to this in general? In general, there are 3 ways you can think of. Well, collapse gas directly into a massive black hole. Instead of starting with a 10 or 100 solar mass black hole seed that in the early universe, maybe there's a way to make immediately a 10 to the 5 or 6 solar mass seed, which we can then use to seed these quasars. Or maybe you can have the stellar mass seed grow by accretion, but then it has to violate this nominal maximum Eddington rate. We have to explain why that happens. Or maybe you just have to merge a lot of, you know, 1 million stellar mass black holes into a single supermassive black holes very rapidly. Now, all these ideas sound very good. They all have obstacles. Roughly speaking, I will go into some details in a second, but roughly speaking, the problem with trying to make 1 million solar mass black hole by directly collapsing a cloud is that that's actually possible in mathematical analysis. If you have a spherical cloud radially collapsing, you can make a black hole. In fact, you know, Oppenheimer worked on this in the 50s, and it was shown that that's possible. But then in real universe, the cloud is never totally spherically symmetric. It has angular momentum in the center of the galaxy. So on the way in, it will actually already fragment into stars and not give you a giant 10 to the 5, 6 solar mass object. So you have to get around it somehow, this fragmentation into smaller clumps. Here the issue is how you evade this Eddington limit, which I'll explain. And then the mergers are also difficult, essentially because because there are too few mergers and I explain this again later. But you'd have to merge. You have to convince 100,000 stars to be in such a dense packed configuration that they all merge into a single black hole. And then remember, every time you have a merger, you get a kick, a recoil kick. And you tend to actually lose black holes due to this recoil, especially at early times when these black holes are sitting in very shallow dark matter potential wells of much smaller than galaxies now, where the escape speeds are much smaller than these recoil speeds. So you can actually very easily keep losing merging black holes. So you have to think a bit harder. And all 3 of these, spoiler alert, are viable. So what I'm going to explain is why they're viable. The overall scheme of things, that they can be made to work, because the early universe is quite different from the present day universe. Essentially, the densities were much higher. 1 plus z cubed is the scaling of the density, not just the background universe, but also the gas collapsing into galaxies is 1 plus z cubed times higher. There are many, many proto-galaxies formed very early times. You can get early start. And most crucially, the gas was chemically very primitive. Question? Sorry, you had a question? Okay, no question. So I think the simplest and most important point I want to dwell on is this collapsing a gas cloud into a black hole and using these features. So just to become again very simple-minded, the first galaxies which form at high redshift appear at about when the universe was 100 million years old, and that's uncontroversial. If you have cold dark matter, you have gravitational instability, you have dark matter halos, which collapse at arbitrary, almost high redshift if you go to lower and lower mass dark matter halos. But you can't actually go to arbitrarily low mass halos. The gas pressure has to be lower than the gravity of the dark matter halo to make the gas collapse with the dark matter. So this is something called the Jeans mass. The Jeans mass is simply where gravitational forces which try to make the gas flow in match the pressure forces which try to prevent the gas inflow. And if you go to larger and larger masses, gravity eventually wins. So if you're above the Jeans mass and you take a spherical region, the gas will collapse with the dark matter. On smaller dark matter halos, the gas doesn't collapse. It just, you get a dark matter halo that doesn't have dense gas in it. And this Jeans mass, when you calculate in cosmology, it's about 10 to the 6 solar masses. So the first time anything interesting can form in the universe is when dark matter halos of 10 to the, comparable to these 10 to the 6 solar masses collapse in the universe, which happens around redshift 30, 40. Now the gas will then collapse with the dark matter, but it will contract, and if you have no radiation of the gas, it will heat up adiabatically in the collapse, and we'll have a temperature that rises up to the so-called virial temperature, which reflects the depth of the dark matter potential well. And eventually, this gas will, if it cannot cool, it just settles into a hydrostatic equilibrium at some relatively high density compared to the background universe, but nowhere near densities of a star or a black hole or anything. So in fact, in order for, well, actually I call these microgalaxies just because the Jeans mass is roughly 10⁻⁶ of the Milky Way. This didn't really catch on. I've been trying to tell people they should call them microgalaxies because 10⁻⁶ of the Milky Way, but this would not actually be a galaxy. It would just be a cloud of gas sitting in a dark matter halo. So in order to actually form a star or collapse the gas to high densities, you have to cool the gas. In the local universe, the process that happens to allow stars to form in a molecular cloud is collisional excitation of molecules and radiative cooling. So again, the process is simply you have some molecules in a galaxy like ours, in the ISM, interstellar medium, there's molecular clouds, CO, H2O molecules, they're very complicated looking. When they collide, they get vibrated or they get excited into rotational and vibrational modes, and then they decay, emit infrared photons which leave the cloud. So you're converting the thermal energy of the gas into radiation. So you're continuously releasing the pressure and the gas collapses. That's how stars form out of molecular clouds, and that's very well understood. The problem is in the early universe, this is the periodic table now, where you have all kinds of atoms and molecules. In the early universe, the periodic table looked very different. We had hydrogen and we had helium before the first stars formed. And that means this gas was chemically very primitive, doesn't have many ways to radiate. In fact, there are only two ways such a gas can efficiently radiate its energy. One is to form hydrogen molecules. The hydrogen molecule doesn't look like this. It's actually just two hydrogen atoms. It's much simpler. It has no dipole moment and is not a very efficient radiator, but it does have rotational vibrational modes. The lowest lying energy levels of the rotational and vibrational modes correspond to about 100 Kelvin. So if you have molecular hydrogen forming in these clouds, you get gas that goes down to about 100 Kelvin. So that's much hotter than molecular clouds, which have these much more intricate molecules, which have many more levels, quantum levels at lower temperatures, lower energies, but it's still relatively cold. If you have no molecular hydrogen, then you cool only by Lyman-Wolf emission. So then you have 8 hydrogen atoms, The first excited level of a hydrogen atom is the Lyman alpha line, which is 10.2 electron volts, which corresponds to 10 to the 4 Kelvin. So if you have no hydrogen molecule, your gas would remain at most at 10 to the 4 Kelvin. You can keep cooling, exciting Lyman alpha radiation, but never below this temperature. So this is the critical point, the temperature. And why is that so, well, why is that so important is what I next will explain. But basically, whether or not H2 molecules can form will control what happens in these clouds. Okay, so how do you, so I'll elaborate on this, but H2 chemistry in the early universe is actually very simple. You have hydrogen atoms and electrons left over from recombination at redshift 1000 in the early universe. You have some electrons, you form H minus plus H gives you an H2. So you can form molecules in principle in the gas. You also can destroy molecules. If you have some radiation impinging on this cloud, you can excite the H2 molecule into a electronic level. So these are UV photons. So, and then this H2 molecule decays back to a split atom. So there's a competition between formation and destruction if you have some radiation impinging on your cloud, which could be coming from nearby objects which already form some stars. So I think I want to not dwell too much on the argument, but I will have to put numbers here. We know the cross sections of these processes. You can evaluate how bright a radiation you need to suppress molecules, and it actually has to be quite bright. It happens, you know, so the bottom line of this is that if you just have an isolated cloud like this, it will form molecular hydrogen, cool down to 100 Kelvin. But if it has a few clouds that did this already nearby and have turned into stars and have UV radiation, then this next cloud is now illuminated and will not have any hydrogen molecules in it. It will just have hydrogen atoms. Why is that so important for our black holes? It's because the inflow rate into these clouds is extremely strongly dependent on the temperature, and the inflow rate will determine the fate of the cloud. So these are hydro simulations, but the simple result is actually written here. If you have a self-gravitating gas cloud with some temperature T, which collapses under its own gravity at this temperature, then the inflow rate simply goes like the sound speed cube divided by g. This is actually an analytic result. It's basically taking this Jeans mass, which is the size of an unstable cloud, and dividing it by the free fall time. Then you can see that if the temperature is hotter, this inflow rate is hotter. So in fact, if you have 100 Kelvin versus 10 to the 4 Kelvin, that's a factor of 100 difference in temperature. That's a factor of 1,000 difference in the accretion rate. This is kind of counterintuitive because the hotter gas actually produces much more rapid inflow. So that can be counterintuitive because you would think pressure is higher. It prevents the collapse, which is actually true. The collapse will take place longer or later, but when it does happen, the inflow rate is much higher because the gas comes in at essentially at the sound speed, which matches the free fall speed. This is a simple result. You can do hydro simulations in cosmological dark matter halos. You can basically just confirm this. If you perform simulations where the molecular hydrogen is allowed to form versus not allowed to form, you confirm the scaling. Oh, I should also say these simulations are, well, I like to make this point that because I give this talk sometimes in galaxy formation context, I actually like to, simulations sometimes have a negative connotation. You're simulating something, you're cheating, you're putting in stuff there that subgrid physics. But this kind of simulations, they're in principle no free parameters. You start from cosmological density and velocity perturbations at some very high redshift when the universe is linear. And then all you're just solving is molecular chemistry and gravitational physics of collapsing gas. So there is no free parameters in principle. Okay. The fate of this cloud, it turns out, is very different, and it's really a switch based on the inflow rate. So I already said in the molecular clouds in our galaxy, you can ask, if you have a core in the middle of this collapsing cloud, which in reality looks something like this, there's a core which gets very dense and is accreting at these rates. Gas is actually flowing in and shocking and heating up to some temperature that's over 100 Kelvin if there's hydrogen molecules, or 10 to the 4 Kelvin if there's no hydrogen molecules. And this core is accreting. If this is a molecular cloud, then it cools to 5 Kelvin, and this m dot is 10 minus 5 solar mass a year. And the mass of, the result of this is a star, which settles on the main sequence. There's a time scale for a molecular cloud core, accreting protostar, to settle on the main sequence of stellar evolution, which is called the Kelvin-Helmholtz time. That's how long it takes to contract the core while it's emitting radiation from its surface, thermal radiation. So if you multiply by 10 to the 5 years, which is this Kelvin-Helmholtz time, you get a few solar mass star, and that's characteristic of stars in galaxies. And then, as I already said, you have a 0.1% chance of a black hole forming at the end of the life of this star. Now, if you raise the temperature to 100 Kelvin, because molecular hydrogen is abundant, then this accretion rate is much higher, maybe 2 orders of magnitude higher. And so the result, and this Kelvin-Helmholtz time scale, it turns out it's actually quite insensitive to protostellar mass. So you still roughly multiply this by 10 to the 5 years, so you get 100 of order 100 solar mass star. These are called POP3 stars, population 3 stars. They're the first stars which form out of pristine gas with the aid of H2 cooling. And the idea is that they're much more massive, typically maybe 100 solar masses instead of 1 solar mass. And so most of them would then give you a black hole, but it's still just a stellar mass black hole. And maybe, 50% is not to be taken super seriously, but it's no longer a small fraction. Now comes the interesting part. What happens if there's no hydrogen molecules? Then the gas temperature remains at 10 to 1000 Kelvin, and the inflow rate becomes a solar mass a year. And now there's actually, this is the key, there's a qualitative difference. You could just say, well, I again multiply this by 10 to the 5 years, and now I have a supermassive star which is 10 to the 5 or 6 solar masses. And that it turns out that gives you a massive black hole. But I want to just clarify the physics of this, because it's, well, just to show you that there are actually calculations here. You can actually do a spherical calculation of a protostellar core, which is accreting at the prescribed m dot, and ask how it evolves. And this shows the stellar radius. This shows the stellar mass. So you start from a low mass protostellar core. This black curve here is the calculation with this called MESA. And you just impose a constant accretion rate of 10 to the minus 3 solar mass per year. So you see the radius of this protostar expands to about 10 solar radii, and then you're accreting. And then here is when you settle on the main sequence and you contract. This is the main sequence. This is a zero-age main sequence, population 3 star. Now, because you contract on the main sequence, you become very compact, and your effective temperature, your luminosity is surface area times sigma t to the 4th. If you're very compact, it becomes the effective temperature is large, 10 to the 5 Kelvin. So now you emit ionizing radiation. And in fact, this calculation doesn't have radiative feedback, but in reality, if you have a protostar which shrunk and now is emitting lots of UV, it will terminate the accretion, because we'll ionize the inflowing gas and blow it away. And that's actually how we understand why the largest stars in the Milky Way are 100 solar masses. They settle on the main sequence and they stop their own feeding due to this radiative feedback. POP3 stars can grow up to 100 or a few hundred solar masses, and then they terminate their own growth. Now look what happens here. If you crank up the accretion rate 0.1 or 1 solar mass array, and again, in order for that to happen, there must be no hydrogen molecules. If you actually realize these high accretion rates, look what happens. You never contract on the main sequence. That's because you're piling on gas, essentially on a time scale that's faster than the contraction time scale. So this star keeps growing, and the radius keeps increasing. You're building the star faster than it could collapse, which means it's always a bloated giant, like a red giant. The temperatures are a few thousand Kelvin. It never emits any ionizing radiation. All the radiation from this blob is in the infrared. And so there's no ionization, no heating feedback, and it can just keep growing. And then once you reach about 10 to the once you reach about 10 to the 5 or 6 solar masses, you could, in fact, some nuclear fusion might still ignite in the core of this, depending on the actual mass accretion rate. But the point is that at 10 to the 5 or 6 solar masses, this is called a supermassive star. At 10 to the 5 or 6 solar masses, a general relativistic instability kicks in, and the entire cloud collapses to a black hole of the similar mass, 10 to the 5 or 6 solar masses. So we should continue this GR instability here, and when you cross that, you collapse to a black hole. That actually has been confirmed in GR-MHD simulations, and even if the star is rotating, for example, you still get half the mass going into a black hole. So I think I managed to hopefully explain this clearly. But any questions on this? So because we now solved our problem, we can actually collapse a cloud. By the way, this is in the literature, people call this the direct collapse model for early black hole seed formation, which I don't like, but I lost this battle. Everybody calls it direct collapse. But since your mind are still open-minded, this is not collapsing a cloud into a black hole. This is collapsing the cloud to a supermassive star, which then undergoes instability to collapse to a black hole. So, and the key is to get rid of molecule hydrogen. And as I explained, that's possible. So the picture is you have these million solar mass seed black holes forming in the rare proto-microgalactic clouds, which are being illuminated by a larger number of earlier forming protogalaxies, which form normal POP3 stars. And these, you can actually count how many of these there are, and because this is relatively rare, but it does happen enough times to explain, for example, these redshift 6 quasars quite easily. So that's one option. We have rapid emergence of these massive black hole seeds at quite high redshifts of 10 or 12. But I think I'm kind of running out of time. So I cannot possibly go into same level of detail about the other ideas. So I think I will summarize mostly in words what happens there. So the second was, I think, how much time? Maybe 5 minutes? This one, maybe I'll skip mostly this, but this one is very interesting, and I promise to explain the Eddington limit and why that can be avoided. So here, it's a separate idea. So we solve this problem by rapid inflow in molecular-free protogalaxy. So the second problem is actually solution turns out quite similar, but the setup is a bit different. So imagine now we have a stellar mass black hole that's accreting, and we're trying to grow it very rapidly, up to at least up to the same kind of seed mass of 1 million solar masses that we can use as a start of all the quasar activity. So there's a cloud collapsing in the middle. There's something like a quasar, but it's a stellar mass black hole remnant of, let's say, an early POP3 star. And the problem is that this disk is emitting, again, UV radiation, which is coming out. And this radiation is basically the inflow rate times the mass of the black hole divided by the size of the black hole. That's the outward going radiation. And then if you say, well, why don't we just make this m dot very large? then we can grow this black hole very rapidly. The point is that at some point, when you grow this m dot very large, it doesn't go into the black hole. The luminosity becomes so large that it exceeds the gravitational force, and the gas doesn't go in. So that's illustrated here. If you try to feed babies, there is actually a maximum rate. If you cannot feed them faster, it doesn't go in, it comes out. Okay, I will skip the math, but the math is actually very simple. Radiation pressure, so you take this luminosity, multiply by the Thomson cross-section, and that's the luminosity, and the radiation pressure will be the flux, which is 1 over r squared times this luminosity at some distance r. And the gravitation force also goes like 1 over r squared. So there's a maximum m dot. Yeah. Yeah. So actually the argument doesn't require this is the argument, it doesn't require spherical symmetry. It just relies on the fact that so let me go through this then just very quickly. So there's a fueling rate on the black hole. Doesn't matter how. Can be symmetric, not symmetric. You're feeding the black hole. The black hole is growing actually by some fraction of this of the inflow rate goes to black hole growth. The other fraction goes to luminosity. Now you have a radiation pressure, which is basically the Thomson cross section times the luminosity divided by 4 pi r squared. No, this can be in any direction. Oh, if the radiation is very strongly, yeah. I will come, well, yeah, you're right. If the radiation is extremely anisotropic, not the feeding, but the radiation. So yes, you could. Okay, that's a good question. So in principle, if your black hole is producing radiation, let's say, only in the north and the south pole, and no radiation comes out at all in the equator, you can feed it in the equator. So that's. Yes. So I think that's actually a very long answer to this, because now you have to ask what happens on large. Then you have to actually ask what happens from large scales down to small scales, and does this radiation impinge on mass, which is feeding the black hole from larger radii? And I don't think that's very clearly known either, how that works. So I'm just talking about this case where the radiation is roughly isotropic, but the fueling can be in any direction. And the point is that you equate this radiation pressure with the gravity, which is gm over r squared. And the point is that if you do that, you get an m dot which is proportional to m, because this L has an m dot times m, this one has an m dot, an m, so m dot proportional to m, which means this is exponential, which means you get exponential growth on some time scale t. This time scale, if you assume a radiation efficiency of 10%, is 40 million years. So this is actually the issue with, well, so this is the Eddington limit. It implies there's this maximum rate, and the growth which would occur between redshift, let's say, infinity and redshift 6, you have 700 million years. The E-folding time scale is 40 million years. If you start with a 100 solar mass black hole, this gives you 10 to the 8 solar masses, which is too small by at least an order of magnitude. Okay. So I just wanted to explain that it's actually possible to evade this limit. Actually, one possibility might be along the lines you're saying, that the radiation is very anisotropic. But even in spherical symmetry, there's an interesting extra physics that happens when the radiation, so this is a picture this is the black hole. This is the luminosity I said, which is coming from few Schwarzschild radii. That's the largest value you can get if you put here a very small radius. And this radiation is trying to come out of the inflowing gas. But this inflowing gas will have free electrons which scatter the photons. And this radiation scatters out. And the idea is that because of this Eddington limit, it stops the inflow on some larger scales. So the only new interesting concept here is this so-called trapping radius. So if the inflow rate is very high and the gas density that builds up here is very high, then the effective diffusion speed of photons outward becomes not the speed of light, but c, the speed of light divided by the optical depth. Again, there's something that is derived in 3 lines. The photons are random walking out, so I think you all have done random walks, and you know that in n steps, you don't go out radially a distance of n times the step size, you go square root of n times the step size. And just from that, you find that if the optical depth is tau, then the effective radial speed outward is c divided by tau. And the free fall speed here, the idea is that close to the black hole, the free fall speed is actually larger than this radial outward diffusion speed, which means up to this radius, the photons, it's like fish swimming in the river upward. They're trying to get out of the cloud, but they're diffusing out slower than the entire cloud is collapsing. So they're advected in, and so the radiation never actually gets out from this region, from inside this trapping radius. So that's the only real new piece of physics. In that case, effectively, the radiation that comes out is not gm.m over r black hole, it's gm.m divided by the trapping radius. Everything here, the black hole eats the radiation. So this is fainter, and in this case, the fueling. So you can do this. We've done this in spherically symmetric and 2-dimensional radiation hydro simulations. And what you find, if this feeding rate is more than several hundred times the Eddington rate, this trapping radius becomes correspondingly hundreds of times larger than the Schwarzschild radius, and the emerging radiation cannot no longer stop the inflow. So the black hole basically swallows all the incoming gas. So that's actually a very interesting new regime. If you have m dot that exceeds the Eddington limit, so again, I don't think I have time to go through details, but in this, when you do a radiation hydro simulation of this, if you impose, let's say, 100 times the Eddington rate, what you find is periodically fluctuating accretion, turns on and off. You fuel the black hole, it shuts down its accretion, then you start fueling again, and it shuts itself down again, and it's episodic with a time average rate that's below Eddington value. But if you make the accretion rate, let's say 1,000 times the Eddington rate, it just, at some point, every feedback stops happening, and you just accrete at the same rate. Black hole eats everything. It's just a free fall because of this trapping. So, and actually, I think I should just contend with this. So basically, the solution here is the same as here. If you have a stellar mass black hole, which finds itself in a galaxy where there's no molecular hydrogen, and the inflow rate is of this value of 0.1 to 1 solar mass a year, that's actually, for a stellar mass black hole, more like 10 to the 4 times Eddington, this maximum Eddington rate, and it will actually be swallowed. So it's actually possible to grow a stellar mass black hole very quickly to a million solar mass black hole this way. And again, the requirement is the same. You want to have no molecular hydrogen so that you have large inflow rate. I think I will skip the last one in the interest of time, and I just say that, well, I don't know what to say in one sentence that would be helpful, but I think I'll just skip this because I don't think I can. I think I would really need some more time to explain. But there's a. I think it's the order in which I listed this is kind of my personal belief of how hard it is to make this happen. So I think this is probably my favorite. This might be a little harder because you want the stellar mass black hole to be in this protogalaxy and still have no molecular hydrogen. So you want no stars to have polluted this cloud, even though there's a black hole there already. So this only happens if your protogalaxy formed this POP3 star somehow, but not produced any metals or pollution or another star. And maybe that's less common than this one. I think this is actually very hard to arrange just because, and basic idea here is that it's these recoils. Okay, I can say one useful sentence, which is, if you go back to my proto-galaxy slide, you can ask a very simple question. These early clouds, when you have a million solar mass dark matter halo, we also know the densities of these halos just from cosmology. The average density in the virial radius, the size of this halo is such that the average density is 18 pi squared times the background density of the universe, roughly 200 times. And so we know the size, so we know the mass and the size, so we know the escape velocity, which is just gm over r square root. And the escape velocities, the one useful thing I can say is that the escape velocities from these tiny microgalaxies is of order a kilometers per second or maybe a few kilometers per second. And the typical recoil velocities for a pair of stellar mass black hole that is merging is hundreds of kilometers per second. So it's very hard in the early universe to retain previous mergers of stellar mass black holes and use them repeatedly to build bigger and bigger black holes. There is a very contorted way out of this, which I will not explain. It requires quite lucky scenarios. And I think I will stop there. Let's see, where's my conclusions? Oh, I should say at least one. Okay, I'm going to show one slide, and that's my last one. I like, where's my, maybe I'll end with this slide. How do you actually figure out how these early black holes formed? Where is my slide? This is my one slide. If you want to probe this early universe beyond redshift 6, and if black holes grow both by mergers and by accretion, I think the best ways to do that are to see both of these. So this shows the reach of LISA, and just to make the point that 10 to the 5, 4, 5, 6 solar mass black holes can be detected out to here redshift 15 at a signal. These are contours of signal to noise for LISA at signal to noise of 100 at redshift 15, 10 to the 5 solar mass black hole mergers. So LISA is a great instrument to probe the assembly in the late stages where the galaxies are slightly larger and can retain these mergers, and down below these 10 to the 5 solar masses. So for example, if all the seeds formed due to this direct collapse rapid assembly, we won't have any mergers here. So if we find with LISA some mergers here, you know that's not the whole story. It's very hard to detect this 10 to the 6 solar mass black holes at redshift 10 or 15 due to their light. The best bet is, so even James Webb Space Telescope cannot really do that. The best would be, that I'm aware of, is this plan to build an X-ray telescope called LYNX. This is its purpose sensitivity to 10 to the 4 solar mass black holes to redshift 15. They would be detectable by this X-ray telescope. So at least that's the basic thing to say, is we can actually probe this population, but not in the next few years, but maybe in the next 10, 20 years. Okay, that's my conclusion. Thank you.
Thanks a lot, Zoltan. So, questions before we go for the coffee break. We are more relaxed today, so we have a normal coffee break. We come back, we have an extended lunch, so don't worry. We have plenty of time for questions. So let me start asking, so in your scenario, in your preferred scenario, let's say, you don't actually expect to see a lot of those intermediate black hole masses. There seems to be two completely different pathways for forming black holes. Supermassive ones, totally independent, and then, you know, stellar mass black holes, and then anything in between, probably you don't form them at all. That's a kind of a prediction then.
So I think you're right about this, just because the temperature bifurcates with or without molecular hydrogen, so it's real distinct. But ultimately, it's not 100% ironclad, because it's not really the temperature that matters, it's m dot that matters. So the question is, can you arrange the m dots that are continuously filling this gap? It looks like when you do hydro simulations, this bifurcation still exists from larger scales into the cores of the galaxy. So I think it is true that you don't form any intermediate mass black holes. There will be, or at least there will be some two distinct populations.
So is it worth doing LISA then? At least for that reason, for those purposes?
Oh yeah, just to check this, yes.
Even if there's nothing there? Well, yeah. Okay, no. That was too much of a provocation.
Well, I should also emphasize that this is just the formation of the seeds.
Yeah.
So after this, they will grow.
Yeah.
So there will be 10 to the 4 solar mass black holes potentially.
Yeah.
From the stellar mass seeds that have grown to 10 to the 4.
Because the chirp mass is still small.
So
it's still, yeah, sorry. So, more questions for Zoltan? Sure.
Thanks, Zoltan, for the presentation. You presented a distribution that looks like a sketch or a cartoon of for the population of black holes from solar mass to stellar mass to supermassive black holes. And I would really like to know, I am very curious, if there is a cutoff for the supermassive ones when you go to the intermediate mass black hole, apparently a gap over there. So in your cartoon, you put like a cutoff, but I don't know if this is a continuum distribution, and it looks like a flat also. I could really...
So you mean this?
Yes, that one. Do you know, well, I think this is just a sketch, right? But I would like to know if there is some, in this population for the supermassive ones, they pile up for the lowest mass, or is there some reference where you can have a slope for this distribution?
Yeah. So I think currently there's no real evidence for a turnover here. That's not explainable simply due to selection effect. The lower the black holes, there seems to be more and more of them, and then you just hit the limit where you can't actually detect them, because these black hole masses, these black holes are found in nuclei of galaxies based on kinematics of the nucleus. And the smaller the black hole, the smaller the angular size of the nucleus. So at some point it becomes impossible to resolve and measure detect the presence of a black hole. So there's no real evidence at the moment of this turnover.
Okay. So we could say that there is, let's say, no gap for the intermediate mass black hole.
I don't think there's any strong evidence.
And in reality, this is not flat, right?
Sorry, this one you mean?
Yes.
No, sorry, this is a sketch. I mean, it does turn over in actual data just because but it's a selection effect. So if you look at the actual number of observed objects, it does stop here and crashes.
Okay, thanks.
But in the range above that, which is resolved, it's not flat. It has actually a -1 slope.